Hi everybody, this is Mr. Folly, and welcome to, wow, disappearing Mr. Folly, Big Idea 5. So we have 5 different lectures that are coming on here, and the problems that go with it from the worksheets that I made. Alright, so here we go. Rates. So a rate is change in something over change in time. Okay, something for us is most often molarity. That's almost always molarity. This is a change in concentration, not amount. So amount, you would think of as moles. Sometimes you'd think of it as grams. Wow, am I getting some weird writing going on? Rates can also be determined by the coefficient of the reaction. Let's see, is there something I can do to maybe? All right, so starting off. So the coefficient, here we go. If 8 moles per second of HNO3 reacts, so 8 moles per second. Hey, that looks similar. And that's going to produce, whoa, okay. Okay, problem solved, I think. How many moles of Cu are required? So moles per second are required. So notice this is going to be 8 up. This is going to be 8, so this is going to be 3. Okay, so that's kind of obvious when we have it set up for that. Okay, how many moles of CuNO3 taken twice form in 1 minute? So if I were to show you how to do that, I suppose I could do 8 moles of HNO3 in 1 second times, and then I would do 8 moles of HNO3 would equal 3 moles of Cu. See how moles of HNO3 would go away, and 8s would cancel as well, so I'd have 3 moles of Cu per second. Okay. How many moles of CuNO3 taken twice form in 1 minute? So what I'm going to do here is I'm going to start with my given, which is 1 minute, and I'm going to change that into seconds. So 1 minute is 60 seconds. And then how many moles of CuNO3 taken twice would form in 1 minute? So, so 8 moles per second are going to happen here. So that means that, oh, I don't like the way I started this, but that's okay. And then I know I have 8 moles of HNO3 in 1 second. So notice how my minutes are canceling. My seconds are canceling. And now I'm in moles of HNO3. And how many moles of that form? So I need to cancel moles of HNO3 and 3 moles of CuNO3 taken twice. So again, notice how all those units cancel, and I'm left with the units of moles of CuNO3 taken twice. But I need a calculator to figure out what happened here, because it's a little more than my mental math can do. So I got 60 times, oh, I guess I could have done this, couldn't I? 60 times 3 is 180 moles of CuNO3 taken twice. All right. How many liters of NO form if the pressure is 1.25 atmospheres and the temperature is 300? So on this one, we get to change it and go back into a little more gassy stuff. So how many liters of NO form? So liters of NO, I've got it right here. So I know I have 180 moles of CuNO3 taken twice. I'm going to convert that into moles of NO. So I'm going to get rid of moles of CuNO3 taken twice. I'm going to go into moles of NO. And moles over moles use coefficient. So I have 2 NOs and 3 of these. And then that's going to give me an answer. So 180 divided by 3 is 60. 60 times 2 is 120 moles of NO. But we want to know liters. So I got to do PV equals nRT. So the pressure is 1.25. I got a point there. Volume is what I'm solving for. N is 120. R is 0.0821 because I'm using liter atmospheres per mole Kelvin. And my temperature is 300. So to solve for V, I have 120 times 0.0821 times 300 divided by 1.25. By the way, I'm getting this from my equation sheet, and that includes this number for R. and my answer for my volume is quite large, but that's because my moles are quite large, 2364 liters. Okay, and everything's 3 sig figs, so I suppose I should say 2360 liters, assuming I've got that as 3 sig figs. All right, the rate of reaction we measure a number of ways. Color change, so colorimetry, we've done that before, which is Beer's law. The following graph was recorded indicating the absorbance of Cu plus 2. So notice this is getting darker because the absorbance is going up. A equals ABC, right? So absorbance is directly proportional to concentration, right? Using the above graph, the slope tells you the relative coefficient. Okay, so copper would have the same slope. So this is Cu plus 2. Okay, so I'm looking at Cu plus 2, which is this, right? So copper would have the same rate because it has the same coefficient, right? Nitric acid would be different, a factor of 8/3. NO compared to this would be 2/3. And water would be 4/3. So copper would have the same slope, different starting points are okay. So I'm going to go ahead and do that. So let's go ahead and make copper. I like to make my copper be green. So I'll start right here. And I'm going to try and parallelogram this. Not parallelogram it, but you get the idea. So different starting points are okay, and there you go. The same slope is what I was shooting for. HNO3 would have a slope of 8/3 larger, and that would be, so if I took this point right here, and it's 1.5, 1.5, and then I would have to make it 8/3 as large. Well, the slope would be 8/3 as large. So whatever the slope would be, I'd multiply the slope times 8/3. Reactants start high and go down. Products start low and go high. So did I do that right? This one started low. Copper plus 2. Copper would have the same slope. Oh no, it wouldn't. So on this, copper is a reactant. So it would start off going, and the slope would be the same. Have the same slope, different starting points, okay, but it would be negative versus positive. And it's really hard to see if those are in there, but you see how these are level, and these are level. That means they're going to equal out at the same time. The pressure of NO gas can be measured, so we can measure the pressure of the gas and how that changes and the rate of that change. So remember how rate equals slope of concentration. Okay. pH can also be measured as HNO3. So it's actually ionized H positive and NO3 negative. pH measures molarity of H positive. So let's take a look. Here's a balance equation. So notice this goes from 0 to 0.5, 0.4. So this shows me that the amount is changing. Okay. So Na plus 1. The coefficient is 2. I'm comparing it to ClO. The coefficient is 2. The change would be the same amount. Hey, that's the same amount. Okay. Cl has a coefficient of 2. The change would be the same amount. So this is delta means change, delta 0.5. I'm going to change my delta to minus 0.5. This side is going to be plus 0.5. 0 plus 0.5 is plus 0.5. Okay, over here, this went down minus 0.1. This is going to go down minus 0.1. This is going to go up plus 0.1. Okay. Now, notice how cobalt's concentration stays constant. This is pretty typical for a catalyst. Catalysts are typically not used up. So if they're not used up, that means they're going to stay constant for the concentration. So note these are all molarities. Questions can be leveled up by giving moles in 2 liters of a solution. So you can mess around with it. So instead of having it be a molarity, you can do moles equals, or molarity equals moles over liters. Or you can change some different things with gases. Catalysts act differently. It may be a surface catalyst, so its concentration is constant. Graph the above many lines, or interpret graphs, many lines should be expected. So notice how Na and ClO negative should have, again, their reactants. They should go down parallel amounts because they have they have the equal concentrations. these two should go up parallel rates. Okay, this should go up at half the rate. I'm very bad at doing half a rate, but you get the idea. And that would be if they're all in molarity. Graphs of a reaction determined by experiment only. So other things don't work. You can't predict it very well. Rates are by experiment only. Often asked. Often missed. Relative rates can be found by comparing coefficients of the reaction. Some reactions that can happen do not happen because they do not have activation energy, which is the minimum energy required for a reaction to take place. This one right here is a big winner. Sometimes it should happen and it doesn't. Be ready for this. Okay? Collision theory. This is the biggest idea in Big Idea 5. This reaches everything. We've talked about it a time or two before. The collision theory. For a reaction to take place, particles have to collide, boom, with enough energy, activation energy, and the correct orientation. Okay? If I change the rate of something, this happens because of the collision theory. So everything must come back to this. So it's typically going to be more collisions or more energetic collisions. Very, very, very rarely will you talk about the correct orientation. And that correct orientation is most often catalysts or often affected by catalyst or nature of reactants. And that just means simple reacts better. And better is faster. Okay. So if I increase the concentration, I'm going to get more collisions per unit time, right? If you heat a reaction, you're going to have more collisions per unit time, more energetic collisions per unit time. Notice how I'm adding per unit time. So a catalyst, less energy is required, so more collisions with enough energy per unit time. Because rate, remember, isn't just product formed, it's product formed per unit time. Oops. If you powder a solid, you have more surface area. So that means you can react in 1,000 places instead of just a few. There are more places for collisions. There's extreme changes in rate. Okay. So for example, right now, if I counted these side by side by side by side by side, there are 6 places where it could hit. When I cut it in half, do you see how I've now added those extra ones, right? Do you see how if I split this one right here, I have plus another, and that's just cutting them a little bit, right? So this is a huge difference. The difference in surface area is enormous. The cube has 6 sides. Cut that cube in half, you have 8 sides, increasing the area by 33%, right? So that's it. And that's it. So we will stop right there. And I will say toot toot toodles.